Well, it may come as a surprise to you that there are a lot of nth order linear differential equations that are not solvable by conventional methods. So it's a fairly easy matter to convert them to a system of first order that we can then solve using Runge-Kutta. So suppose we've got a linear initial value problem, right? The nth derivative of x with respect to t is some function of t times n minus first derivative plus another function of t times the n minus second derivative, all the way down to a function of t times the first derivative plus a function of t times the function itself, plus some other function f of t with initial condition when x of t0 is some constant c0, x prime of t0 is c1, x n minus 1, you know, that should be the n minus first derivative, so hang on a second as I straighten this out. Oh dear, I didn't mean to do that. Okay, I think I've got that fixed. The n minus first derivative at t sub 0, sorry, need that in there too, at t sub 0 equals c n minus 1. So we got n new variables. If we just say let x1 of t be x of t, x2 be x prime, x3 be x double prime, etc. xn of t is the n minus first derivative of x with respect to t. So now we've got this huge system of equations. The derivative of this is x2, that's x prime, remember. The derivative of x2 is x2 prime, see how that works, etc. Finally, the n minus first or the derivative of x sub n minus 1 is xn, which is this one. And finally, the last equation, which is really the only equation, is the nth derivative, is our function of t times x sub n of t, that's this one. See, that's really just this derivative put in there. And then this one, same thing, times xn minus 1. So we just move right on up the ladder and have all these covered. And so that is our new equation. But see, this is a system, all these differential equations, and we're going to have one for every order. So if it's an nth order, we're going to have n of them. And so x prime, the vector x prime, equals matrix A of t times vector x plus some vector f of t, whatever this is. Of course, it's only going to show up in this one, so f of t is going to be 0, 0, 0, 0, 0, 0, 0, 0, 0, f of t. So here's our x vector. Here's our f of t, as I said, 0, 0, 0, 0, 0, and f of t. And then finally, here's our matrix A. Now it's one off the diagonal, and then finally the last row has all these functions in it. Oh, looks like I got I have an a sub 0 in here, and I'm thinking I don't have a 0. Yes, I do. I have an a0, and this is an a1, so I must be off by 1. I'm sorry to say. So this should be a1. This should be a2, and we go over to n minus 1, and that's good. And here's our vector of initial conditions. So this, I'm not going to make one with order bigger than 2, but here's our second order linear differential equation, and I know, yes, we can solve this in the usual way. y0 is 1 initial condition, y prime of 0 is negative 4 in initial condition. And so how do we use Runge-Kutta to solve this? And remember, solve is producing a table of values. So we start by solving for this. So y double prime equals negative 2y prime plus 8y plus e to the t. So we define y0 as t is y, y1 of t is y prime, and then we have a system of first order linear. See, instead of having a second order equation, we have two first order equations, and one of them says y prime of 0 is 0 times y0 plus y1. Because remember, y of 0 is y, and y1 is y prime, so this is saying y0 prime equals y1. Of course, that's what this says. Y prime is y1. And y1 prime, that would be our second derivative, is 8. Actually, we could get that from this. Y1 prime is negative 2y prime plus 8y prime plus e to the t. Sorry, this is 8y, and how did I miss that? This is negative 2y prime, but y prime is y1. So I think you should have that all right. We got everything. This is 8 times the original function y. This is 2 times y prime, which is y1. And initial conditions, we have a vector of initial conditions. Y0 is 1, y prime is 0 is negative 4, so that's the initial condition. So how do we set this up for Runge-Kutta with MathCAD? And granted, you might be able to do Runge-Kutta systems with Wolfram Alpha. I haven't tried it, but you know, it might be something you might want to try just for your own interest's sake. So we say here's our C, here's our differential equation. See, here's y, here, that's this, and this set up as a vector. And so we do our solution. The table of solutions is RK fixed, C, which is our initial condition. Remember when we did this way back here, right? Initial conditions, and was here, and x goes from here to here with 10 steps. So we got to do the same sort of thing with our system. Here's our initial conditions. X goes from 0 to 2, 2.0 with 20 steps in there. So why am I going to 2.0? Because we wanted to find, oh, did I say produce a solution? And no, I didn't say how far to go. I should have said that. We're going out to 2. We're going to see, we know what y of 0 is. We want to know what's y of 2. So that's why this 2 is here. And the d is, of course, our derivative vector. This is like the x prime equals, you know, that. And so here's our solution table, and this is x at 0, x at 1, x at 2, and you should see at this point our solution, except you don't, because we got to go out to 20th step. So here is our solution for this one, 16.719. Now I haven't solved this equation. I don't think it would be terribly hard to do with a non-numeric method. It's a second order. Would it be hard or easy? It would have a oh, it'd be kind of easy, I think. So all right, I wasn't going to do that, but I'll do that. But I'll make one more video so we can check our answer to see if we're getting something that's pretty close to what that really is.
I'm going to make them an offer he can't refuse.
Okay, so they made me an offer I can't refuse. I'm going to actually solve the equation and compare our solution to the answer that's listed with our Runge-Kutta method in another video.